I'll record too. Okay, hi everyone. It's our great pleasure to have Dominic Else, who will tell us about diabolical critical points. Dominic, please take it away.
Okay, great. Yeah, it's great to be invited to speak to you. Um, Sorry, I saw a raised hand, but maybe that was a mistake. Um, yeah, so I'll explain what the title means in due course. So I know there are people with a range of backgrounds here, so if anything is not clear, please speak up. But first, I want to start with this concept of a phase of matter. So you have your Hamiltonian. I guess it could be a quantum many-body lattice Hamiltonian or maybe a quantum field theory. And it depends on various parameters. I wrote, parameters of Hamiltonian. You can also imagine that something like temperature is also a parameter. And then you can plot, the phase diagram as a function of the various parameters, and you'll see maybe that there are different phases of matter that are separated by phase transitions. And phases of matter, really, they are like sharply distinct things. Like, a famous example is like solid versus liquid. A solid spontaneously breaks spatial symmetries, but a liquid does not. So if you want to kind of move in parameter space, going from a solid to a liquid, at some point there needs to be a sharp phase transition where the symmetry is restored. So because these phases have different character, they're always separated by a phase transition. And another way to think about these phase transitions is they're actually defects in parameter space. So specifically, it would be a codimension 1 defect in parameter space. So you have these phases, and then at the phase transition, something singular happens, and so you can think of that as kind of defect. And it's defects that kind of have to be there for kind of topological reasons because they separate different phases. And so why do I say codimension 1? Well, the dimension is not really an invariant quantity because it depends on how many parameters you've included in the Hamiltonian, because you can always add additional parameters. The codimension is a thing that's kind of invariant under adding extra parameters. And so, for example, if you have only one parameter, then a phase transition is dimension 0. If you add a second parameter, the phase boundary will become dimension 1. But it's always codimension 1. So that's the invariant thing. And then just to clarify, I'm talking about defects in parameter space. I think this audience may be particularly accustomed to thinking about defects in space-time because that's related to generalized symmetries. That's definitely not what I'm talking about today. I'm talking about defects in parameter space. Now, in many cases, there are some relations between defects in parameter space and defects in space-time, but not always. So you have to keep in mind it's a different thing. Anyway, so this raises the question, if a phase transition is a defect of codimension 1, can you have defects of higher codimension? And so, for example, you can consider if you have two parameters, maybe there's a codimension 2 defect, which would be like a point. And so this point will be where there's some single behavior happening. So what exactly I mean by single behavior could depend on the context. So one example would be that maybe for all values of the parameters except for point, you have a ground state that's gapped, and then it becomes gapless at the singularity. So that's one possibility. You could also have cases where maybe the whole phase diagram is gapless, but then there's some other behavior that happens at this point, like it's described by some different universality class, for example. The other thing I want to say is that to really call this like a topological defect in parameter space, there should be some kind of non-trivial winding as you go around. Just as like in this phase diagram, there's a topological reason why the codimension 1 defect has to be there because it separates different phases. For this higher codimension thing, there should be some topological reason why that singularity has to be there. And so there'll be you want to say that there's some kind of non-trivial winding number as you enclose this singularity. Winding of what? Well, I'll explain as we go, but like basically you're probing the pi1 of the space of non-singular many-body ground states, or you could also say thermal equilibrium states at non-zero temperature. And again, what I mean by non-singular will be context dependent. Like it could mean gapped, or it could mean like described by a particular universality class or something like that. And so how can this happen? Well, there are some famous examples. For example, we have the Fowler's bump. So there's different ways to think about the Thales pump, like from the lattice perspective or from a quantum field theory perspective. So here I'll start with the continuum version. So for example, you can consider a Dirac fermion in 1 plus 1D. So in 1 plus 1D, there's like two fermion modes for right moving fermions psi r and left moving fermions psi l. And then you can switch on a mass term, which actually couples the right moving and left moving modes. And the mass term, the mass you can write in general can be a complex number because it's m and then just add m star here. So the mass term you can treat as a parameter, and because it's complex mass, it has two real parameters, real and imaginary part. And so we know that at the point where the mass is zero, the system is gapless, otherwise it's gapped. And indeed, it's the case that if you surround this gapless point, if you wind around this gapless point, there's some kind of non-trivial winding associated with that. And so how do you probe that? Well, suppose, let me write the mass term in polar coordinates. And I'll assume that the magnitude of the mass is greater than zero. So we're sitting away from the gapless point. So now I can couple to a background gauge field for the global U1 symmetry. So this system has a global U1 symmetry where it will rotate the phase of sort of psi L and psi R. It's like the vector U1, if you want to call it that way, because the axial U1 is broken by the mass. So as a global symmetry, you can couple to a background gauge field. And then you can integrate out the fermions because they're gapped. And so then you can say, well, what is left after you've integrated out fermions? You can get a quantized topological term that involves the gauge field. And if it was just involving the gauge field, that would be like saying you have a symmetry protected topological phase. But you can also get these topological terms that also depends on the parameter. So here it would be like AD theta. And this term, you can argue from gauge invariance is quantized. So the fact that you get this quantized topological term is the manifestation that there's some kind of non-trivial winding in the space of ground states as you encircle this gapless point. And so this topological term has various consequences. For example, if you take like a space-like surface, you can compute the total charge, which is proportional to the winding number of the theta. You imagine that you take theta to be spatially dependent in this setup. You can also compute you can take a time-like surface, and then you can compute how much charge moves through that surface over some time-dependent process. And that's also proportional to the winding number of theta, but in time. So anyway, there's also physical consequences you can derive, but the main point is just that you have this non-trivial winding. So this gapless point really has to be there for topological reasons, as long as you preserve this global U1 symmetry.
Can I ask a question?
Oh, yes.
In this example, if you restrict to the real axis, you have an extra symmetry that is time reversal. So in principle, you could eliminate one dimension from the phase diagram by imposing time reversal, and then this defect becomes of codimension one. So is this a general feature of the story that you're going to discuss, or is just something that shows up in this particular example?
Well, I don't think it's generally true that there's always going to be some symmetry. Often if you have symmetry, it may like reduce the number of parameters that you can vary. But I don't think there's any general statement about that.
Okay. Okay, thanks.
Right. So yeah, this gapless, yeah. And so, this is one example. There's a pretty general theory that's being developed for these like topological families. And you can do it over any parameter space. So like in the Thales pump, we just did it over a circle, but you can do any parameter space X. And so you can think of it either from a quantum field theory perspective in terms of these like topological terms, or from the more microscopic point of view in terms of like the actual quantum many-body ground states on the lattice. Well, it's believed that the classification should be the same. And so there's various works on how that classification ends up happening. So I don't want to talk too much more about that in this talk. One of the main points is going to be to show that there's a different kind of topological family that you can have that's not covered by any of these works. So these topological families are for like ground states. of quantum many-body systems. Generally, you don't get any such families for like classical stat-mech systems or like finite temperature systems. But that will not be true for the new kind of families I want to discuss. So I want to discuss topological families that occur in the presence of spontaneous symmetry breaking. And these ones can happen even in like classical stat-mech systems. So just to recap, what is spontaneous symmetry breaking? Well, basically you assume the Hamiltonian has some symmetry, but either the ground states or the thermal equilibrium states fail to have that symmetry. They only have some smaller symmetry, H, which is a subgroup of G. And then you say, well, how is this possible? The only way it can happen is if there's more than one ground state or more than one equilibrium state, and then the symmetry acts on the space of ground states. So there's a collection of equilibrium states, and the collection is labeled by this order parameter space, which is just G mod H. And then so these states get permuted by the action of the symmetry. But if you look at individual state, it's not invariant under G. And so just a simple example is the Ising ferromagnet. So this is a system where you have spins that can point up or down. So there's an Ising or Z2 symmetry, which is where you just flip the spins. And then you can imagine spontaneously breaking that symmetry down to nothing. So H is 1, in which case the order parameter space is just 2 points. But in other words, there's 2 ground states or 2 equilibrium states, which get permuted by the symmetry. And so physically, you can think of as basically an insuitable parameter regime. The spins want to be aligned with each other mostly. And so you get 2 possible equilibrium states, one where the spins point mostly up, and the other one where the spins point mostly down. The symmetry will permute these 2 states. But the system, if you have an actual system, it'll just choose one of these 2 states at random. And so it looks like the symmetry is being broken spontaneously. So that's spontaneous symmetry breaking. Now, oh yeah, and of course there are other examples that are famous, like for example, the Heisenberg ferromagnet, where the spins can point kind of in any direction. So you have an SO3 spin rotation symmetry, and then the spins choose a particular direction to point in. That breaks the symmetry spontaneously down to SO2 because you can still do a rotation about the axis of the spin. And so the order of space is the quotient SO3 mod SO2, which is the same as the 2 sphere. And so the ground states basically correspond to which direction of the spin you've chosen, which lives on the 2 sphere. But coming back to this case of Z2 spontaneous symmetry breaking, the question I want to ask is, can you have suppose that in parameter space you have some singularity, and then you move around that point, can you have any kind of non-trivial winding taking place? And the answer is yes. And so the way it ends up happening, so we imagine that we can move around this circle. Now, for a particular value of the parameters, so it's Ising spontaneously, or it's spontaneously broken Z2 symmetry. So there's 2 possible ground states you can have, which the system just chooses randomly, and they're related by the Z2 symmetry. Now imagine that we move along this circle. So we're tuning the parameters. For different value parameters, there's also 2 independent ground states, because we assume that like everywhere on this phase diagram, except maybe at the singular point, you have Z2 spontaneous symmetry breaking. But they're not the same ground states, right? Obviously, the ground states are going to depend on the choice of parameters. But if you kind of move continuously, there's always a way to the ground state should evolve continuously as a function of the parameters. So there's always a way to say that if I continuously deform the parameter, the ground states get continuously deformed along with them. And so you can say that this ground state corresponds to this ground state, and this ground state corresponds to this ground state. So locally, you can always do such an identification. The question is, if you do this process, you move continuously around the whole circle, and you keep track of how the ground states transform, what's going to happen? So there's 2 things that can happen. One of them is that the ground states just go back to the same ones that you had to begin with. And the other one is that the ground states actually get exchanged after going around the circle. So there's this Z2 classification of families, which is just corresponding to like the permutations of 2 points. So either they don't get exchanged or they do get exchanged. So if you have this non-trivial one, where the non-trivial family where the ground states actually getting exchanged, implies that there must be a singularity inside, because yeah, because there's some non-trivial winding number.
Dominic, quick question. So before you were talking about the homotopy groups of the coupling constant space, but certainly this can't be because of some pi one of Z2 because that would be trivial.
I said
So
homotopy groups of the space of ground states, not the coupling constant space. I mean,
ah, it's, I see. But still, here the space of ground states is V2.
no, the space of ground. Sorry, for a given parameter value, the space of ground states is Z2. But I mean the space of all possible ground states for all parameter values. And when here by ground state, I mean like the ground state space. Ground states up. So for each parameter value, there's a twofold space of ground states. But then I'm then saying you take that space for all possible parameters, the union of that space for all possible parameters.
I
So the
see.
space of all possible twofold degenerate ground states.
I see. Okay, thanks.
Right.
Sorry, maybe I missed something, but what are these two parameters here? Aren't temperature and magnetization?
Well, I'm talking in abstractly here, so I'm not specifying what the parameters are. I mean, in the next slide, I'm going to have a concrete model that like implements this family, if that's what you're asking about. But I mean, here I'm just reasoning in an abstract way. We suppose we have some parameters that you can tune, and there's some non-trivial winding as you go around. But if you want the concrete model, that's on the
Ah, I
next
see.
slide.
I see. So you're not talking about the Ising model now.
No, maybe the terminology is misleading. By Ising SSB, I just mean that we have a Z2 symmetry to spontaneously broken, not the actual Ising model. No. Right, so yeah, so maybe this is clearer if we consider the concrete model. So the way we'll do it is basically we consider a rotor model. So we'll have some 1D chain. Well, we can do it in high dimension too, but just we can do 1D. And then each lattice side of 1D chain, you put a rotor variable. So that's an angular variable phi I. So angular just means that you identify phi I and phi I plus 2 pi are the same. And then you can write a Hamiltonian involving those variables. So we have this cosine term. The cosine term just basically wants to make all the rotors like pointing the same direction. You want to make phi I equal to phi I plus 1. And then we also have this other term. So cos to phi minus theta. Theta, which I put in red here, is the parameter that we're going to tune. So now, so this cosine term breaks for U1 symmetry, but you still have a Z2 symmetry because you can shift phi by pi, right? And this Z2 symmetry is actually getting spontaneously broken. So we can compute the ground state of this Hamiltonian, which is easy because it's kind of classical, like all the terms commute. So we basically just minimize the energy of each term individually. So the first term just makes you want to have all the phi's be equal, and then this term, second term, will determine what the like lowest energy value of phi is, which you can easily solve. You see phi I is either theta over 2 or theta over 2 plus pi. So there's a twofold degenerate ground state, and indeed it spontaneously breaks the Z2 symmetry because the Z2 symmetry exchanges these two states. So Z2 symmetry is spontaneously broken. But then you can say, well, what happens as you tune theta? So we can, theta itself, you can think of as an angular parameter. So it goes from 0 to 2 pi. So when theta equals 0, the ground states are phi equals 0 or pi. But then you continuously tune theta until you get to 2 pi. So you go from 0 and pi to pi and 0. In other words, the ground states have gotten exchanged. So this is precisely implementing this non-trivial winding that I was alluding to in this concrete model. Yeah, so I can, yeah, right. The ground states get swapped as you verify from 0 to 2 pi. That's what I said. So we can kind of develop a general classification for these kinds of things. I will first specialize to the discrete case. By discrete, I don't mean that the groups have to be discrete. I mean that the order parameter space lambda should be a discrete space. So basically, the point is that like if you go around the circle, you can induce a permutation of the ground states. And ground states are labeled by the space lambda, so it's a permutation of the space lambda. There's one wrinkle here, which is that because we assume that all Hamiltonians are G-symmetric, the G symmetry is getting spontaneously broken, but it's not explicitly broken, so the Hamiltonian still respects the symmetry. So any kind of deformation that you do has to respect the symmetry. So we have to restrict ourselves to only allow G symmetric permutations. So these families of a circle are classified by the space of G symmetric permutations of this space. So for the Z2 case, the G symmetric condition didn't really make any difference. But like you can think about, for example, if you have a Z free symmetry that's spontaneously broken, neither you would say the space for all so there's free ground states. So neither you would say the space of all possible permutations is S free, but most of those are not actually invariant under the action of the symmetry. So it's actually only like the cyclic permutations that are permissible. So you get a Z-free classification of families. There's also some math you can do that says this group of G-symmetric permutations actually can be written just as this kind of algebraic thing. You take this subgroup H, which is the residual symmetry after spontaneous symmetry breaking. You compute its normalizer, which is the largest subgroup of G, such that H is a normal subgroup. And then you compute this quotient. Anyway, that's a math statement. Okay, so that's the discrete case, but now we can also generalize to like the non-discrete case. If you know anything about fiber bundles, you may be looking ahead to what the answer will be, because this situation with the discrete case is basically like a fiber bundle with a discrete fiber. So the general situation is that so suppose we have a symmetry G is spontaneously breaking down H. So you have some lambda space that labels the ground states, which could be a continuous space. You can think about Heisenberg ferromagnet, for example, where lambda is a two-sphere. So the idea is that the space of ground states forms a fiber bundle. And the base space of that fiber bundle is a parameter space. And the fiber is lambda. So for a given value of the parameters, you have a space of ground states that's labeled by lambda, so that's the fiber. But there's not necessarily a canonical way to identify the space of ground states for two different parameter values. So that's kind of the nature of what a fiber bundle is. You have to specify the transition functions. And so one thing is that whenever you talk about fiber bundles, you should ask what the structure group is. That's like the thing that the transition functions live in. And it's similar to what I said in the discrete case. Basically, for a general fiber bundle, you can the structure group could be like a general homeomorphism of the fiber, but you have to impose this G symmetry condition. So instead, we can do only the space of G symmetric maps from lambda to itself, which I call G hat. And again, it can be written in terms of this normalizer thing. So the situation basically is we have a fiber bundle, and its structure group is this G hat. So it's kind of a general statement about fiber bundles that once you specify the fiber, the only thing left to specify is the transition functions, which is the same as the data of a principal G hat bundle. Right, so our main result is that these spontaneous symmetry breaking families are classified by principal G hat bundles over the parameter space. And of course, if you restrict to, like, for example, the discrete case that I mentioned, you will get back to what I said before.
So I have a quick question. So when you're talking about the parameter space, is this the true parameter space, or is this the parameter space with some special points and lines carved out where things are gapless?
Well, the latter, except that, as I mentioned, the gaplessness, you carve out singular points, which may or may not mean gapless, depending on context. But right, it would be like you want to carve out the singularities. Yeah.
Okay, so this is only for codimension 2.
No, this is for arbitrary codimension. I mean, the codimension does determine what you should take to be what the topology of a parameter space will be, right? Like if for codimension 2, a parameter space will basically be like homotopic to a circle. For high codimension, parameter space will be homotopic to some higher sphere, higher dimensional sphere.
Okay. But this isn't for the case where you have like multiple varying degrees of codimension singularities.
Multiple degrees of codimension singularities.
You can have like some lines, you can have some points, you can have some surfaces.
Right. Okay. But in that case, you sort of, I think what you expect is that like you should be able to like focus on each singularity separately and say like what is the winding around that singularity, right?
Does it depend on solving the Hamiltonian?
Well, if you, I mean, if you actually want to say for a given like Hamiltonian, what kind of singularities do you have or what kind of windings do you have, then obviously you need to solve the Hamiltonian.
No, it's a
Classification is
follow-up
an
on
abstract
my
classification.
my question is a follow-up on Sal's question. You said that you carve out the singularities. In order to know what to carve out, you need to know more details
Hmm.
about the Hamiltonian. In particular, where is the system going to be singular? Is it when your parameter is 7 or maybe when it's 5.2?
Sure, you need to know where the singularities are, certainly, yeah.
But that's almost the same as solving the system.
Yeah, I'm not sure I take your point. I mean, you always have to solve a system to know what the system does. I mean, it's same for like topological phases, right? We can do a classification of topological phases, but like if I give you a Hamiltonian and say which topological phase it is in, obviously you have to have a way to solve that Hamiltonian.
No, but here you need something more detailed. You need to know where the singularities are.
Right. You have to solve Hamiltonian as a function of the parameters. Yeah.
Okay.
Right. So, okay. I mean, this is abstract, pretty abstract in general. Maybe it's helpful to think about examples. Of course, I talked about this Ising or Z2 example previously, but another nice example, which is where the order parameter space is actually continuous, is the case where you have a U1 symmetry that gets spontaneously broken down to nothing. This is what we would call a superfluid, right? In that case, you can easily check that G hat is actually just the same as G, which is U1. And suppose we look at a parameter space S2, which is like, if you want to study a codimension free defect, that would be the thing to do. Now you have to say, what are the classification of principal U1 bundles over the two sphere? Well, I mean, this is a famous result. There's a Z classification. If you think about this principal U1 bundle as being like a U1 gauge field, you could call that a monopole, right? I don't think you should physically interpret this G hat as being like an actual gauge group. But anyway, there's a mathematical statement that principal U1 bundles are Z classified over the two sphere. And physically, if you did interpret it as a gauge field, it would be a monopole. So the conclusion is that superfluids support a codimension free topological defect in parameter space because you can have a non-trivial winding over the two sphere, which is classified by Z. This kind of thing was also discussed from a somewhat different perspective in this paper by Sun and Masieko. So again, if you want a concrete model that realizes that, I can do that. So let's take a 2D lattice system. On each lattice site, I'm going to have a classical degree of freedom, and that classical degree of freedom, rather than being just a rotor, which would live on the circle, that classical degree of freedom will live on the free sphere now. And the free sphere, you can also parameterize it by saying that it's a complex two-dimensional unit vector. So right, is a vector Zi, which is a two-dimensional vector, complex vector. And then I can write a Hamiltonian that looks like this. So again, the first term just kind of forces all the Z's to be the same in the ground state. And then the second term will actually select out which the value of Z is the lowest energy. And these N is a three-dimensional real vector, which is the parameter space. So sigma is just like regular Pauli matrices. So this model always has a U1 symmetry because you can just rotate the phase of the C. But in the ground state, it's going to pick out a particular value of Z. So the symmetry gets spontaneously broken. And you can see that as you wind, so there's a single point at the origin. So if you set n equals 0, then you have a larger symmetry group. So it's sort of in a different universality class. So that's what we call a singularity. But if you wind around the origin in this three-dimensional parameter space, you indeed get this non-trivial winding over S2. to get this non-trivial principal U1 bundle. I mean, mathematicians also call this like it's the Hopf vibration. But anyway, so the point is that there is this non-trivial topology, and so that gives you this singularity with non-trivial winding surrounding it in a superfluid. So there's more examples you can consider. For example, the Heisenberg ferromagnet, which I mentioned before, where you break SO3 down to SO2, you get a two-sphere order parameter space. You can show in that case the G hat is actually just Z2. And if you think about how this G hat, remember, is the space of like G symmetric homeomorphisms of the order parameter space. So in this case, it's actually basically acting like a time reversal symmetry, in the sense that it sends, if a spin points in one direction on the two-sphere, it sends it to the antipode. But an important thing to note, though, is that Heisenberg ferromagnet doesn't need to have time reversal symmetry. So this G hat is the group of this fiber bundle. It doesn't need to represent an actual symmetry of the problem, which is interesting, I think. And that's kind of what tells you that there isn't this one-to-one correspondence between these phase diagram defects and defects in space-time, because defects in space-time would correspond to the actual symmetries, and G hat is not a symmetry. But yeah, because this G hat is Z2, again, you can get this Z2 classification of winding over the circle, if the parameter space is a circle. And it's a similar story with this time reversal invariant superfluid. So then you have U1 semi-index Z2T gets broken down to Z2T. Again, the G hat is Z2 in that case. So this was also discussed in Sun and Massiaker. Yeah, so that's about all I wanted to say about this spontaneous symmetry breaking families. I can open it for if there are further questions on that.
I have a question. So you gave the nice stylus pump example and you showed the invertible theory way of viewing it. Is there a similar invertible theory way of viewing these examples?
Well, I don't know, because like the phase itself is not invertible, right? Spontaneous symmetry breaking phases are invertible. Yeah, so I don't know.
But I don't. I mean, I imagine what one could do is what you did in your earlier papers, where you imagine, like, weakly explicitly breaking the symmetry, gapping out the goldstones, and then going through having your like tuning your parameters, going through gapped Hamiltonians now instead.
Um, I'm not sure if you really want to do that in this case, actually. I mean, maybe you could do that, but the important point is that for each value of parameters, you still have this like space of states, right? So it's not just a single state that's evolving as a function of parameters. It's like fiber, which is lambda, which is like evolving with the parameters. So I think it's a bit different.
I see. All right, thank you.
Okay, anything else?
Also, I have a question.
Yeah.
If you were to look at a defect parameter space instead of the space of parameters of the Hamiltonian, and look at the similar, like higher codimension defects in the defect parameter space, how much of the story would change?
Sorry, maybe I'm not sure what you mean by defect parameter space.
So, like, let's say a conformal manifold.
Yeah, I'm not too familiar with those kinds of defects.
Okay, thank you.
Okay, let me talk about diabolical critical points, which was the title of the talk. So first, I want to come back to this idea of phase transitions. So what I've talked about so far is more like kind of a higher codimension classification of the phases, because I haven't said much about like what the nature of the singularity between them is. So when you have two phases, the phase transition between them is also something that's interesting to study. I mentioned it's a codimension one defect in parameter space, but there's different kinds of phase transitions. You can have first ordered phase transitions where some local operator changes discontinuously as you cross the phase boundary. Those are kind of more boring kind of phase transitions. But then there are more interesting kind of phase transitions, which are continuous phase transitions. And so continuous phase transitions have a lot of interesting stuff going on. They have correlation length diverging, which means you have an emergent scaling variance. There's critical fluctuations, and as well as fluctuations on all length scales. There's universality classes, critical exponents. Yeah, so many things you can say about continuous phase transitions. From an RG perspective, a continuous phase transition, at least if it's stable, would like an RG fixed point that has a single relevant direction. So you add the relevant operator, it'll drive you into one phase of the other phase, depending on its sign. So that would be like a continuous phase transition. And so I want to kind of answer this word problem. So continuous phase transitions are the most interesting kind of phase transitions. So continuous phase transitions are to phase transitions as what are to defects of higher codimension. And so the answer is this diabolical critical points. So this term diabolical points we got from this paper, which was also talking about these topological families. I think it's kind of terminology that's inherited from much older literature. But we inserted this word critical because I think the most interesting things about these things is the emergent criticality. So diabolical critical points is what we call them. So in the RG perspective, a diabolical critical point of codimension K would be an RG fixed point that has exactly K relevant operators. So I guess this picture would be like the case where K equals 2. But it's not just that, because you want to say that once you add the relevant operator and then you wind around the critical point, that there must be some kind of non-trivial topological family. And it could be either this like spontaneous symmetry breaking type topological families that I mentioned in the first part of the talk, or it could be this like invertible families of the Fowler's bump. And so in terms of a phase diagram, you would see that there would be a point of codimension K, and then it would be which you would have like all these critical behaviors like divergent correlation length, scaling exponents, etc. And it would be surrounded by some non-trivial winding. And that non-trivial winding serves to explain why the critical point had to be there, right? Because the non-trivial winding means you cannot eliminate the critical point for topological reasons. In the same way that a continuous phase transition has to be there, well, it doesn't have to be continuous, but at least the phase transition has to be there because you're separating two different phases. It's an outer statement of that. But I want to emphasize that like a diabolical critical point is not the only thing that could be inside a topological family. So there's different possibilities. Just as like in the case of phase transitions, you can have like first order or continuous transitions. I mean, there's also different possibilities that could happen in this high codimension case. So one thing that could happen is just to have some intermediate phase. So there's some region here, and you just undergo a phase transition as you go into that region. So then there's no diabolical critical point here. It's just the intermediate phase. And also possibilities you could have like a first order or continuous phase transition that sits inside the family. I put phase transition in quotes here because, by the nature of this phase diagram, you see that this phase transition is not a transition between two different phases, because it's actually the same phase because you can just go around. Nevertheless, you can still get these phase transitions even if it's separating just the same phase. Like famously, like the solid to liquid is not an example of this, but the liquid to gas transition is an example of this, because liquid is actually the same phase as gas. You can just go around in a phase diagram and connect them continuously. but there is in some parameter regime a phase transition between liquid and gas. So that's kind of like this. In the case where it's a continuous phase transition, people have also called this unnecessary quantum critical point. Although in this kind of context, in some sense, it is kind of necessary in the sense that there had to be some kind of singularity if you're inside a non-trivial family. But anyway. And so the point of this kind of scenario is that the codimension of the phase transition of a singular points is not maximal, right? Because here we had some non-trivial winding of a circle. So the maximal codimension of the singularity would be a point. Well, in two-dimensional parameter space, it would be a point. In general, it would be codimension 2. That's the maximal codimension. But this singularity has codimension 1, not codimension 2. So it's not the maximal codimension. So we reserve the term diabolical critical point for the case where it actually has the maximal codimension that's compatible for winding. So if you have a topological family over the circle, the maximal codimension is 2. If you had a topological family over the 2-sphere, the maximal codimension would be 3, etc. So that's what we think that we actually call diabolical critical point. And so you can, for example, study, once you have some model that has a non-trivial family, you can kind of study what happens inside the family. And so an easy case to consider is the case of this C2 spontaneous symmetry breaking family. So remember, I wrote down this model for that. You have these terms like this. It's kind of more convenient to rewrite this cos in terms of coses and sines. So I'm going to write cos 2 phi and sine 2 phi. And so now I have parameters A and B. So I can draw the phase diagram as a function of A and B. And so when A and B is 0, then your model actually has U1 symmetry. So that's kind of a different universality class. So that's what we call the singularity. It's sitting on the origin. But then if you encircle that point, you get this non-trivial winding that I mentioned, where the ground states get exchanged. But this is kind of fine-tuned in the sense that, you can, there's arbitrarily many more parameters you can add to the Hamiltonian. So let's just add one, which is like cos 4 phi. And so I'll call that coefficient A prime. So this is for A prime equals 0. But now you can study the phase diagram when you switch on a non-zero A prime. And what actually happens is that this singular point actually expands into a first-order line. As you cross this first-order line, the ground value of phi in the ground state actually changes discontinuously. So this is example of this scenario that I mentioned previously. Like, it looks here like you have a diabolical critical point, but it's not really very stable because you add extra parameters, it kind of generically becomes this first order line, which is not maximal codimension. And this seems to be usually, at least in these kind of classical models at 0 temperature, that seems to be usually what happens. You can check that in this model for the topological family of superfluids, which was a codimension free defect, it's a similar story. You generically get this like first order surface of codimension 1. But let's come back to, suppose we did have a diabolical critical point, what properties would it need to have? So when you have a continuous phase transition between these two phases, say like spontaneous breaking phase or trivial phase, or between two topological phases, it must be the case that the properties of those phases somehow get imprinted on the quantum criticality at the phase transition. So I want to say that something similar will happen for these diabolical critical points. If you're surrounded by a topological family, the singularity must in some sense have critical fluctuations that are imprinted upon by the nature of a topological family. And so to understand how this might occur, it's kind of helpful to go back to the case of phase transitions between phases of matter. So the codimension 1 case. And so let's think about phase transition between a trivial phase and an invertible topological phase. And so there are some papers that looked at this question. And the idea is that there should be an emergent symmetry at the phase transition. The details actually depends on whether the topological phase is order 2 or not order 2 under stacking. The order 2 case is kind of the simplest one to think about because that's where you get a emergent Z2 zero form symmetry at the critical point. So that's at the critical point between these two phases. Otherwise, it's anti-unitary symmetry. And so this is the case of invertible topological phase. You can also think about the case where you have a symmetry protect topological phase. Then you have the same statements, except that the anomaly will be a mixed anomaly with the protecting symmetry. And so why does this have to be true? I don't think there's a rigorous argument. In fact, you can sort of construct, I think there may be some loopholes to this argument, but anyway, heuristically, the idea is just that at the level of quantum field theory, there should be a duality transformation that corresponds to just stacking with an invertible topological phase. And so if the topological phase is order 2, the duality transformation should be order 2. Now, in general, that won't be a symmetry, right? Because it'll change you from a quantum field theory to a different quantum field theory. For example, it will take you from the trivial phase into the invertible topological phase and back. But you kind of expect that at the phase transition, it should become a symmetry. So you would expect that you get an emergent Z2 symmetry at the phase transition. And then you can show that this, if it's true that this symmetry corresponds to stacking with an invertible topological phase, it actually has to be anomalous. So we expect there to be a similar story for these diabolical critical points. But how would that happen? The naive expectation, which is what I kind of thought would happen when I first started thinking about this problem, is that instead of emergent zero form symmetry, you should have emergent high form symmetry because it's associated with like defects of higher codimension. But that doesn't work because the whole point of this scenario is that we want to say that there's some emergent symmetry at the critical point, and then you add the relevant operators and it breaks the symmetry down to something else. So certainly that's what happens in these examples, right? The Z2 symmetry is anomalous. So in order to get like a gap phase, you have to break the symmetry. But this can't happen for high form symmetry, right? Because high form symmetry is by definition, there are no local operators that don't preserve the symmetry. And so there's no relevant operators that could break the symmetry. So that's not the answer. The answer seems to be instead that you should have an emergent symmetry, but it should still be zero form, but it should be continuous zero form symmetry. So one thing that I could mention is that in a certain sense, having a continuous zero form symmetry is kind of like having a higher form symmetry. If you think about the point of view of classifying spaces, the classifying space of U1 is the same classifying space for a Z1 form symmetry. So like from a homotopic perspective, that they are the same. I don't quite know how to interpret that statement because a U1 symmetry is very different from a one form symmetry. So if there's any experts in the audience who can shed light on this, but in any case, there's some kind of similarity between continuous symmetries and high form symmetries. And in the case, from a point of view of like the properties of these diabolical critical points, it does appear that a continuous zero form does the job. And so you can think about, for example, this case of a Fowler's pump. So it had a global U1 symmetry throughout the phase diagram, but at the diabolical critical point, so I mean, you can verify that just by power counting, that this mass term is the only relevant operator. So this indeed will give you a diabolical critical point, which is stable, unlike in this spontaneous symmetry breaking example that I described. And so this diabolical critical point, it does have an emergent symmetry, right? Because at the diabolical critical point, you turn off the mass term, so then you have this kind of axial U1. In other words, you can rotate the phase of psi L and psi R independently. So microscopically, you only have a U1 symmetry, but then at that critical point, you have a U1 times U1 symmetry. And this U1 symmetry times U1 symmetry is also anomalous.
Sorry, one question.
Yeah.
By analogy with what you just said about having continuous symmetries, do you expect that in codimension 3 you should have infinite dimensional symmetries?
No, it doesn't have to be infinite dimensional. It ends up being basically, so here the emergent symmetry is like U1. For codimension 3, you expect something more like an SU2 symmetry or something. So it's just a high dimensional Lie group, but doesn't need to be infinite dimensional.
Okay.
Yes, so this anomaly is this emergent symmetry anomaly. It seems to indeed be related to the topological family you get once you add the relevant operators. So I cannot prove for you that diabolical critter point has to have an emergent continuous symmetry. As I mentioned, even the proof of this continuous phase tension case, I think you can't really rigorously prove that the C2 symmetry has to be there, or at least I haven't seen such a proof. But what I can say is that if you do have this emergent symmetry, then you can show how it's related to the topological families. So suppose that we have a diabolical critter point which has an emergent continuous symmetry, and then you add the relevant operator that gets broken down to some subgroup of that. You can, in general, predict like which topological family you get. So a simple example is the case, suppose we have an emergent symmetry U1, you add the relevant operator that gets broken down to Z2, and then that gets spontaneously broken. So now in terms of the families, you'd be back in this like Ising spontaneously breaking family case. Well, there's a parameter space which is the quotient of these two groups. Basically, it's in terms of like it's basically the space of ways you can add the relevant operators. So the parameter space is the quotient U1 C2, which is a circle. Another way to think about it just is that you have there should be two relevant operators because you want to here you want to diabolical codimension 2. So if there's two relevant operators, then the space of relevant operators you can add is R squared. And then you take out the origin, which is singular, and you're left with something that's like homotopic to the circle. But the point is that because this parameter space can be written as this quotient, it must be the case that you get this non-trivial family over S1 as opposed to the trivial family. So the ground states will get exchanged. Basically, because if you think about going over around this circle in parameter space, it's basically like acting on the ground states of Z2 because you form the circle as this quotient. And so you necessarily, in this scenario, get the non-trivial family over S1. So just from the structure of the emergent symmetry, how it gets broken, you can predict which family you will get. In this case, you see the emergent symmetry doesn't actually have to be anomalous. It just comes from the algebraic structure of the group in this case. And so we've also discussed this for this Fowler's pump case. So there's an anomalous, the U1 times U1 symmetry is anomalous, and you can actually show that if you add the relevant operators to break it down to the diagonal U1, you necessarily get a Fowler's pump with respect to that diagonal U1. And that just follows directly from the anomaly. So there's actually a general theory we developed in this paper to relate the anomaly of the emergent symmetry to the family you get upon breaking the symmetry down. It turns out you don't always have to have an anomaly. I mean, I mentioned this spontaneous symmetry breaking family, but even for this invertible topological families, you actually don't always have to have an anomaly, but there's some general compatibility relation that you can construct. Okay, so yeah, so the reason why this talk was called In Search of Diabolical Critter Points was basically that we didn't have that many examples. So I mentioned this Dirac fermion in 1+1D, which is an example. You can also talk about Dirac fermions in higher dimensions, which would be examples too. But they would correspond to like pumps of like quantum Hall states. There's another example, which is the SU2 Western-Witten CFT in 1+1D. You can think of that as a codimension 4 diabolical critical point. So that kind of addresses this question of what happens with high codimension. You can have just like an SU2 symmetry in that case. Yeah, but there isn't very many examples. So what I was hoping is that because we have an idea of what properties they should have, right? In terms of emergent symmetry and anomaly, in terms of number of relevant operators, it kind of seems like a good candidate for conformal bootstrap methods because, I mean, assuming that there's some like emergent Lorentz invariance of a critical point, it would be a CFT because it also should be scale invariant. So then it's just a question of saying, is there a CFT which have these kinds of properties? And so that's the kind of question that Bootstrap is designed to address. So I hope that maybe Bootstrap will allow some more constructions of these kinds of things. But anyway, I will conclude there. Yeah, thanks for listening.
All right, thank you, Dominic. Any questions? I can ask a first question. So it seemed like oftentimes you're looking at a linking sphere, but do you have any examples where you don't look at a linking sphere, but you look at some other, something else? Like for example, maybe you have like a line, and instead of looking at a linking circle, you look at some torus. Uh,
Well, okay, so the certainly the family classification, you can do it over any space, right? Like it's five. So it's in spontaneous breaking case, it's fiber bundles over the parameter space, which is general, and then there's something also in the case of these invertible topological families. So that you can classify in general. I mean, but generally in the context of these like diabolical critical points, like because this idea of a diabolical point should be like an RG fixed point where you add some number of relevant operators. In some sense, the natural parameter space to think about is always like R to the n, punctured in some way, right? You can't really have an analog of diabolical root point that doesn't involve just some kind of sphere, which would be like a punctured plane or punctured R to the n. So if you have a family over some space which isn't just like a punctured R to the n, the question of what is inside it, it's a little bit more. You can't really be just a diabolical critical point. Unless, I mean, it could be that you have a family over torus, but then it's also like a family over a sphere, and then the diabolical point sits inside the sphere. But if there really is like a family over some other manifold which isn't reducible to a family over some like n sphere, which I don't know to what extent that can happen. Anyway, if that was the case, then the question of what would be inside would be more complicated. I think it wouldn't just be a diabolical critical point. It couldn't be.
Just a small comment. The only other examples I know of families which are not over spheres are over these projective spaces. So, for example, you'd consider two sphere, but identify the antipodes, so then you'd get a family over RP2 or something like that.
mm. Any other questions? All right. Well, if there's no other questions, let's thank Dominic again, and I'll stop the recording.